welcome back. We are in lecture number 2 on weathering and erosion. This will be about 4 different lectures on this topic. It's all in chapter 5 in our online textbook. Last class we introduced you to the concept of weathering, then we did chemical weathering, and today's topic is mechanical weathering. It's a little bit bigger of a topic, so it's going to just be standalone. Mechanical weathering is the physical breaking down of rock into smaller pieces. It's the actual physical breakdown. Chemical we were dissolving, usually with water, but here we're going to physically break into smaller pieces. Water is going to be our main actor, but other things will as well. Within this topic of mechanical weathering, I'm going to give you 2 different lists. The first is agents, and the second is going to be let's see, what could we call it? It's going to be classification. So to start, let's talk about our agents of mechanical weathering. I don't need to write the whole thing over. Agents of mechanical weathering. Sorry for wasting time there with that. This is a list of 4. The first type of agent is going to be impacts. Collision upon collision upon collision. Particles banging into particles, maybe at the bottom of a stream, or sand blowing across a desert. This is going to lead to abrasion and the reduction in particle size. So for impact, we're just going to say collisions abrade during transport. Imagine a river in full flow along that riverbed, all right? This is at a flood stage, right? On the hydrograph, we learned about that. We've got all these rocks bouncing around as they're moving, being moved as bed load, and as they bang into one another, they're going to break off chips and pieces of each other, making them all smaller, and we're going to get a grain size reduction. So the agent of change here is impact. Number 2 is wedging. I like the name wedging. Wedging means gradual cracking. And what I'd like you to imagine is you're walking on a sidewalk and there's a tree nearby. You've seen how the roots of the tree will break through the sidewalk. That is biologic wedging, root wedging. And just like it happens on an asphalt or concrete, it also happens in a rock. So if you wanted to try to draw that or mention that as an example, that is a great thing to do. So wedging is going to happen with plants. We could either call it root wedging or biologic wedging. Ice will do it. And sometimes salt will, if you're near the coast. I'll just insert a picture here showing ice wedging. Water during the day, when temperatures are hotter, will percolate down into cracks. But then when night comes, the water freezes to ice. There's a volume expansion of 9%, and it will make a crack. And then the next day, it makes the crack a little bigger and a little bigger and a little bigger. Right? There's our schematic, and here is a good example from some frigid terrain where this boulder has been slowly broken apart by water percolating in and ice freezing. All right, that's agent number 2. Agent number 3, pressure expansion. This might be the hardest one to understand. Rocks are under huge amounts of pressure when they're underground. So here's, let's say, a frozen magma chamber, and it's deep underground. There is huge amounts of pressure on that are keeping everything together. But then as erosion occurs, how do I do this? Let's say we erode, and we erode, and we erode, and we bring that closer to the Earth's surface. There is now much less pressure. Let's say much less pressure than there was initially. Because there's much less pressure, this is able to expand. And when it expands, cracks start to form. And that is the breaking up of rock. So that's my schematic sketch. Let me try to give you some words for it. When erosion overburden removed releases pressure on a rock body. When you release that pressure, we say cracks can occur. Not only can they occur, they want to occur, and they often occur. Very similar to pressure expansion is thermal expansion. And this is when heat causes the rock to expand, and it's a solid. So even though it's expanding, it's a solid, and solids don't want to change their shape. And so in order to accommodate that expansion, they crack and they pop. And that's what thermal expansion is. So in a lot of ways, this picture would apply to thermal expansion. It's just volume increase. Okay, increase. And this is usually during the diurnal cycle, daytime to nighttime. During the day, a rock in Texas is 100 degrees Fahrenheit, but during the night it cools down to 70. Well, the temperature difference between night and day can actually create that volume expanse that's enough to create cracking. So volume increase due to heating and cooling. So during cooling it'd be a volume decrease, leads to cracking. And so these are the 4 processes where we're actually going to crack and break a rock down to sediment. Now for our second list today, I want to go through how do we actually describe our sediment that is produced by those agents. And so this heading is going to be sediment classification. And this is going to tie into sedimentary geology, because people who study sandstones and conglomerates, the sedimentary geologists, they use the same kind of classification for loose sediment as they do for an actual rock. And so there are 4 different ways that sediments are classified, and the first is by particle size. There are tiny particles and there are large particles. The size of a particle depends on the energy that was transporting it. And so we should say something here about when we describe a sediment, we are also geologically going to be very interested in the carrying capacity of the fluid that was moving particles of this size. And so I'm going to call this as a proxy for energy. A high velocity stream with a lot of energy can move big particles. That's what we're getting at here. And so our list of particle sizes, there are official names for this and size cutoffs. What I want you to know for this class is that there are boulders, and there are cobbles, and there are pebbles, and there are sands, and there are silts, and then there are clays or mud. And so I'm not going to make you memorize the size threshold for this. You will in a later class if you're a geo. Basically, a boulder is anything bigger than your fist. A golf ball would be a cobble. A pebble would be something like a bean or a pea. A sand is a sand. Now for silt and mud, they're smaller than what you can really see with your naked eye. So what we sometimes do in geology is we put them in our mouth and we grind it between our teeth like toothpaste. And if it's a little bit gritty, then it's a silt. And if it's smooth between your teeth, then it's mud size. And this has to do with the centimeters and millimeters of the different particles. All right, the key here is that it's a proxy for energy. Where would slow moving water land? It would be down here. Slow Mississippi kind of river would be depositing silts and sands. Pebble, and this would be something like on a beach or on a medium-sized river. And boulders and cobbles, we're talking massive floods, or something like an ice with a glacier that could be carrying boulders and cobbles. All right, that's particle size. Number 2 is sorting. This is like Harry Potter, right? With the sorting hat. What we're going to do here is we're going to sort, though, instead the grain sizes. So it's sorting of grain size. And what sorting is, it's a measure of homogeneity. Said another way, it's a measure of heterogeneity. How similar, how mixed things are. So if something has a high degree of sorting, that means it is not mixed. Everything is the same. And if and actually the word that we use for that is we would call that one well sorted. A sketch of something well sorted would be like a sand on a beach where every grain of sand is like almost exactly the same size. Or every cobble on a beach is exactly the same size. And if you have a very low degree of sorting, then you are very mixed. All the sizes are mixed in together. We use the phrase here, poorly sorted. And for poorly sorted, if we were to make a sketch, we would draw big things. And those big particles are mixed in with super tiny particles, and the whole range is there together. An example of a low degree would be till from a glacier. The till from a glacier is mixed from clays to boulders, all being carried by the ice. Now, sorting is also a proxy for energy. Something that has a lot of energy is able to mix a lot of things up together. Lower energy systems tend to have a better degree of sorting. All right, now what do we got next? Number 3 is rounding. Rounding is our proxy for transport distance. And rounding is a measure of angularity. So we could have something that is very angular versus a particle that is smooth and round. And so what we would be able to say, if we had sand grains of these 3 different shapes, this one has traveled no distance. So we could say no travel. It's near the source. The corners have not yet been abraded off. And then this is medium travel, and something round and polished and smooth has been transported and transported and transported. So all the corners have been chipped away. So we could say long travel. Or we could sketch this in another way. How about here's a mountain range going down into the ocean. Where would you expect each of these things? Well, something that has traveled a long way and is well-rounded would be closer to the flat line area. Medium is less, and then no travel is up in the source. Angularity tends to be near the source where there hasn't had an opportunity to have collisions. We could also say rounding is the sum of all collisions. I'm going to put in a picture here that talks about 1, 2, and 3, or let's see if we can see 1, 2, and 3 in this picture all by itself. So if we're going to look for particle size, sorting, and rounding, all in this one picture. It's a picture of a sedimentary sequence. We have a geologist looking at it, and my eyeball sees is I see sandstones that are fairly fine-grained. I see conglomerates. So here we're seeing a difference in particle size from the sandstone up here to the conglomerate. I also see a bunch of boulders and cobbles at the top of this horizon, and I see smaller gravels below. We can describe this outcrop with respect to particle size. And you see the layers. Now another thing, let's see. Look at the big boulders. Look at this one in particular. That is well-rounded. This one is moderately well-rounded. In fact, most of these boulders that I'm seeing are smooth in their shape. And so we can see a degree of rounding in the larger particles. And then now sorting. The sand bodies down here and up here, these are all sand grains, so they're well sorted. But in these horizons, I see a mixture of gravels, cobbles, and probably smaller than what I can see on the screen is sands. So we have some horizons here that are poorly sorted, and we have some horizons that are well sorted. So those are ways we can walk up to an outcrop of sedimentary rock or sediment and describe it in 3 different ways. Now this list was number 4. And so the 4th way that we describe sediment is with this word provenance. Provenance means your origin, where you come from. We all have different origins, or where we're born and where we've lived. Well, same with sediment. And so provenance means origin of material. And geologists are trying to find out where the source material was for some particle to unravel some problem that they're working on. This can be a fascinating topic, and here's our example that I'd like to give of provenance. This just came out here, this is a lecture that I'm giving here in 2024. It's September right now, but in August of 2024, on the cover of Nature, the best of the science journals, there's a picture of Stonehenge. And there's, let's read this right here. Scottish origin for Stonehenge altar hints at societal organisms, blah, 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 blah. This is an article about provenance where they were trying to figure out where the altar stone comes from for Stonehenge, because Stonehenge is down here. I don't know if you can see this, but this is like Great Britain, and Stonehenge is located in the south. But geologists realized a long time ago the stones that make up Stonehenge don't come from the south; their provenance is from somewhere else. And so this study from 2024 actually tracked, look at this, altar stone source from way up here. And so the scientists, that's a big discovery. But then what it also tells us about human history, and that back in the day, the people were able to transport huge rocks with some degree of technology, maybe by ocean, right? I don't know which way they did it. Probably by ocean. They probably didn't drag this across all of Great Britain in order to take it to this location here in the south. All right, that's provenance.